Okay, this is section 9.1, Introduction to Statistical Tests. This is probably the most important thing that we cover this semester straight out, is because this is what we can use to initially make any statement about anything that we want to look at statistically in any scenario we want. So like our final projects and things like that, this is what we are going to use. So hypothesis testing, like I just said, is used to make decisions concerning the value of a parameter. Now hopefully by now we understand a parameter is a population-based number, whether it's a mean, a standard deviation, or anything else. And most of the time we talk about the mean or the average, and what we want to do is decide, is it significant or not? Is it true and accurate to what people claim it is, or are they kind of giving you a line of you know what? So null hypothesis. How is this thing set up? Okay, H and then the subset 0, H of 0 is what we kind of show or denote our null hypothesis. What is a null hypothesis? It's the working hypothesis about the population parameter in question. Basically, it's what they state. It's what's happened in the years past. It has no effect or no difference, or hasn't changed. So what we're going to try, and I'll show you what the null hypothesis is. It's basically the all the last 19 million years or whatever is your null hypothesis. And then your alternative or your alternate hypothesis is kind of what you think is going to happen. It's anything that's different from it. It's the statement that you will adopt should you decide to reject the null hypothesis, and I'll show you that. And this thing's denoted with an H of 1, or hypothesis 1, or it's the alternate. So that's what I'm going to show you is, but we're going to name it as this is the null hypothesis, and then this is going to be your alternate. Alright, so one example, here's just kind of a thing to do. If you're driving on Highway 10 out of Moorhead or whatever, maybe the miles per hour is 65 miles an hour. And that's the miles per hour that should be done, and law says that's what's happening. So that's going to be your null hypothesis. And what we want to do with these null hypotheses is, if we think there's something statistically different than it, we want to list it as what we think is happening or has happened forever, or what the law says. And then what we're going to do is, if we think people speed on this road, okay, I think the cars on that road go faster than 65 miles an hour. My alternate hypothesis is going to be the mu is greater than 65 miles per hour. Okay, so the null hypothesis is always going to be equal to some specified number, and then your alternate's going to be different from it. So it might be greater than, like this one, it might be less than, and it could be just straight out different from, and we'll have a two-tailed test. So here's another example to let us kind of understand what's the null and what's the alternate hypothesis. Manufacturer claims their light bulbs burn for an average of 1,000 hours. And we have reason to believe the bulbs do not last that long. Okay, so just from that piece of information, I want us to learn how to set up a null hypothesis and an alternate. The null, what do they claim? What's their overall manufacturing thing? The mu is equal to 1,000 hours. That's what they claim. Okay, but we have reason to believe that bulbs just burn out way too fast and they do not last that long. If that's our claim, we'll say the mu is less than 1,000 hours. Okay, so that's kind of the idea. Can you take out what number basically the manufacturer or anything gives you, and the null will always have an equal to sign by it, and then the alternate's going to be kind of the claim we think is happening. We're not positive, we need to do the test, but that's what's going to happen. Okay, now I'm going to just cover these briefly. There are two types of error involved, so you can technically be wrong in what you have, and that's why we always have the different confidence levels and things like that. So you could end up rejecting the null hypothesis when it's actually true. So example is, if I go back here, I could say that the light bulb is different from 1,000 hours when in fact it really does burn exactly 1,000 hours. So there is that possibility. That's what we call type 1 error. Type 2 error would be actually not rejecting it when it's actually false. So maybe I say that, hey, yeah, this company's sweet. They actually do have light bulbs that burn for exactly 1,000 hours, except if I make that statement, but that's actually different from, maybe they do burn out less than it, that would be a type 2 error. Now, I'm not going to cover it a lot. It's not a huge deal. because I want us to understand the concept of actually hypothesis testing in this section more so than figuring out type 1 and type 2 error. Okay, so this goes back to if it's true and you actually reject it, okay, and so on and so forth. There's different levels. Now, I'm not going to cover this much more either, but we have what we call an alpha. Alpha is our pivotal number. It's our level of significance. And in this section, it's going to be between 1% or 5%. Okay, and what that does is, are we going to give ourselves a 1% chance to be wrong or a 5% chance to be wrong? And there are different levels and different things that we can do. And that's how we'll kind of show this. So, just another example. I want you to just figure out what's the null and what's the alternate hypothesis. So fast food restaurant indicates an age of its job applicants is 15 years old, and we suspect that the true age is lower than that. And we want to wish the claim of significance at a 1% level. So this is kind of the problem that you're going to read. When they say this level of significance at 1%, that's how much error we're going to have. This is my magic number. Okay, and I'm going to talk about that magic number a lot more in a little while, but every problem you need to figure out these three things, and that's why I want to practice this. The null hypothesis, what does this restaurant claim? The age, average age, is 15 years old. What do we feel is? We feel, I believe, that it's lower than 15, so less than 15 years old. And the other thing I'm going to want you to list is that my alpha is 1%. You need to list these three things every single time you do a hypothesis test. And that'll be points on each problem on a test or a quiz or anything else. So that is very important. Okay? Now the different types of tests, I've kind of mentioned this a little bit. Left tail test is what I've actually kind of shown you with the hypothesis more so than anything. What we're going to do is we're going to look for the probability, the number, in the left tail, because it's a left tail test, because it's less than. Okay? If I would do a right-tailed test, I think that my null hypothesis is greater than my alternate. Okay, then it's a right-tail test, and I'm going to look for the information in the right tail. And you're going to go back to Chapter 5, Chapter 6, when we started getting into z-scores, things like that. These same ideas happening. Now, a two-tailed test is when I don't care if it's greater than or less than. I'm just looking to see if it's different from. So I'm actually going to look for information in both tails. So I have two examples, I believe, that I'm going to show you. Okay? Oh, before I get to those examples, I should probably talk about these values. Okay, the probabilities. Now, hopefully all of us can be on the same page and say, when I go to my z table, I know that when I find the number in my table, it's a probability. So maybe it's like 0.0132. Okay? That number from your z-chart, which by the way you're going to need that, refers to what we call the p-value, the probability of this scenario. Okay? And what I'm going to do is compare this number to that alpha number. And I'll kind of talk about that in a second. Okay? So we're going to kind of see, is it extreme? Is it beyond what we think is our limitation or our error area? Now, how do we kind of compare this? And I'd rather get to the example and then explain to you. You should recognize this. This is right on your formula sheet, the first formula in Chapter 9. Okay? Just know that X bar is your sample or our test statistic. Mu is the overall population. That's kind of the big, broad statement that they give you. This should always be your null hypothesis every time, whatever that mu value is. And then n will be given to you, and in this section, when I know the population standard deviation, that means I'm going to use a z-score. I will also give you that sigma. Okay? So when you get into it, I'm going to actually come back and refer to this slide to tell you, okay, if that p-value we find is less than a, we will reject. If it's greater than, we're going to not reject. So what we need to do is try set up a problem. I want to give you an example. So suppose that Sam, who's always been a 250 career hitter, works hard during the winter and the off season, and he thinks he can now bat 333. Okay? So he's going to raise his batting average from 250 to 333. So instead of getting a hit 1 out of every 4 at-bats, he's going to get a hit 1 in every 3 at-bats. And what the manager is willing to do is coach says he'll move him up in the batting order Okay? If he can prove his new batting average within 30 at-bats. All right? So based on practice observation, they give you sigma, which by the way is important for later. That's your population standard deviation. They just want you to test that the claim that his batting average has improved. Okay? So here's what we need to talk about. The first three things before you even worry about the whole scenario, what's your null hypothesis and your alternate. The null hypothesis is he's always been what? A 250 career hitter, or a 250 hitter. So 1 out of every 4 at-bats this guy gets a hit. Alright? What does he believe with all of his hard work? That his average is going to increase. Now be careful. I just care that it's going to be greater than 250. You do not need to state anything about the 0.333 in your null or alternate hypothesis. He's just claiming that he's going to go up, and he just randomly, arbitrarily picked this number. We do not need to even use that number in our null and alternate hypothesis. Your null hypothesis will be the number that he always was, and then you're either going to be greater than or less than or different from the null in your alternate. We don't have to statistically prove that he actually got to 333. All right? His level of significance. What's my magic number? 5%. So what I want to see is, did he actually get that? And that's what I want to know. So how do I figure this out? We need to find a z-score. Now if you find your z-score, x bar minus mu over sigma over the square root of n. So your x bar, this x bar is what this guy believes he can do. 333 minus your mu, which is your null hypothesis, over sigma, which is 0.20 from way over on the right, divided by how many at-bats? 30. And what that ends up being is a z-score of 2.27. Now all of you should now be able to go into your table and find the z-score of 2.27 and give me a probability of that happening. Now here's what's tricky. Here's what you got to think about. I think of a curve. Now I'm going to try to draw this out for some of you. Z equals 2.27. And if you go to your table, you're going to get a number of 0.9884. That's the probability. If you go to your z table and you look up 2.27, you get 0.9884. Now remember, z-scores give you everything to the left. What did the alternate hypothesis tell us? That we are looking to see if this guy's batting average improved. It's greater than. So this is a right-tailed test. So we want the information to the right. So how do I figure that out? Now hopefully we can all say, oh yeah, I just need to go 1 minus. So if I go 1 minus the 0.98, that's 0.0116. So the probability of him having a greater than 250 average, okay, actually getting a 333, the number that we find in our table is essentially about 1.16%. Okay, so that is what we call our p-value. So in this problem, whatever number you basically find from your table in the correct tail that we're looking for becomes your p-value. And that's the number I'm going to compare to my alpha. So in this problem I had 0.0116, and I want to see if it's less than or equal to 0.05, or is it this one, 0.0116? Is it greater than or equal to 0.05? Which one is true? Okay, it's less than. This is significant because we are in a tail. Our number gets us to a tail beyond. Now I kind of think about like control charts and stuff. This is like beyond 2 or 3 standard deviations. It's a warning sign. It's significant. We need to look at it. If it is less than your magic number, okay, since it's less than 0.05, it's statistically significant, which means we can reject it. And our claim, or this kid's claim, is very true. So what I'm going to do once I say I reject the null hypothesis, okay, because 0.0116 is less than 0.05, I can reject the null hypothesis, and like chapter 8, you need to give me a sentence. What does this mean? Now basically you need to include at the 5% level of significance, but I'm not going to write of significance, there is enough evidence to suggest his batting average is... Now, what did the alternate hypothesis? We are rejecting. We're saying that he no longer has an average of 250. We're saying that his average is greater than 250. You do not say that it is exactly 333, because that's not necessarily true. We have enough evidence in our little sample to say that it is greater than 250. It might be 252, it might be 300, but we just know that it's greater than 250 at this significance level. Okay? So that's how you finish the problem. Now, some of you are going, oh my goodness, this is crazy. Well, let's try one more. I'm going to try to do this one a little bit quicker. So what you need to do is read through it. So we're looking at an ammonia, nitrogen concentration in a river. And I'm kind of cutting this stuff off, I see. But for many years, the concentration was 2.23. That's telling you what your mu was. And now there's a new golf course, a new housing development, and this is causing concern because of fertilizer, and they think there might be a change in this nitrogen level in the river. So it says, based on recent studies, and that X is normal, here's your sigma that'll be given to you. That's a key that it's a z-score. Let's use a sample of 8 water tests, and it gives you these values. Now notice I do not give you an average in here. So what do you think you have to do to find the X bar of this sample of 8? Okay, you're going to actually have to dump it into a calculator, add them up, divide by 8. I'll tell you right now that it's 2.51, and you can check it if you want to. And I need to construct a statistical test to see if the concentration has changed from 2.3. Now remember, the 3 things you need: alternate, a null, okay, null, alternate, and then your alpha. Well, the alpha is 0.01 this time. They are claiming that historically it was 200 or 2.3 milligrams per liter, and we are looking to see if it has changed from. It doesn't say lower than, less than, higher than, greater than, or anything, which means that my alternate is just different from that value. That's my alternate. I just think it's different from, and that's what I want to see. Has the fertilizer or these new places changed it? So how do I do that? I need a z-score so I can find a probability. Now I'm not going to write the z-score formula down anymore, but X bar, which is these numbers, these were the 8 we found, 2.51, minus my mu, which by the way the mu is your null every time, over standard deviation, which was 0.30, divided by the square root of how many samples did we take? 8 of them. And if you calculate that z-score, you get 1.98. So now if you go to your z-table and you find that number, now I think it's different from. Now if I go to my z-table and I have a 1.98, that's over here somewhere, which means I get the number, what is it, 0.9761, all the way to the left. The problem is this. I want mu is not equal to, which is different from. I need my 2 tails. Alright? This 0.9761 gives you all the information from this line all the way left, which means the right tail is 1 minus that. Okay? 1 minus that is 0.0239. Now I not only want the right tail, I want the left tail, because this could be less than. We didn't know that off the bat. So we need to do, now this is symmetrical, so twice as much of this number will also be there. Okay? So what we need to do is just to find our p-value. This is only going to happen, the only time you have to multiply by 2 is if it's not equal to, if I want both tails. So I'm going to go 2 times 0.0239. And that gives me a p-value of 0.0478. Alright? So we no different than the first problem. We found a z-score. But the only difference about this one than the first one was only a one-tailed test, the right tail. So whatever number I got on that right tail was the number I compared to my alpha. In this problem, I had a two-tailed test because I was looking for the left and the right tail. So when I found one of the tails, I had to multiply it by 2. Okay? And I got a p-value of 0.0478. Now when I compare 0.0478, that is greater than my initial alpha of 0.01. So if I go back to this page, what happens when my alpha is greater than? So I had 0.0478 is greater than 0.01. I do not reject. Okay? So how do I state this? I can write do not reject the null hypothesis, and then at the 1% level, what can I state? There's not enough evidence to claim what? That there's any difference. Not enough evidence to suggest any difference in the nitrogen levels. Okay, so this time there really wasn't any difference. So I just gave you an example when you do reject and one when you do not reject. Okay, couple things to think about. If you fail to reject, okay, we basically just state that the null hypothesis is not changed. Okay, it's not that we've proved it to be true beyond all doubt, but it's just we have not proved it to be any different. If you do reject it, like we did on the very first one, we choose the alternative hypothesis and the understanding that we have not necessarily proved, for instance, the batter that he's actually hitting 333. We just know that it is different beyond all doubt right now. Okay, so we'll talk about those wording and different things like that. Here's the assignment that we're going to have. Hopefully you can kind of work through this, and we will try to fix all up the missing links in class. Hope you have a great day.